Now we have already seen that slope of straight line is constant for selection of any 2 points on it. Now consider graph of one function like this, which is not a straight line, in fact it is curve. Now for this curve, slope is not constant for selection of any 2 points. For example, if we join these 2 points, then we get here value of tan theta. Suppose we join these 2 points on curve, we get value of tan theta, or say tan theta 1 from this triangle. We can see that the value of tan theta 1 and tan theta is not same. So how to get slope of curve at any point? Now slope of this curve changes from point to point. It is not same for selection of any 2 points. Now consider this diagram in which we have a graph of function y is equal to fx. Here we are joining points P and Q on the graph. When any 2 points on the graph are joined, that line is called secant line. Or we can say this is chord of curve. Now suppose abscissa of point P is x and that of point Q is x plus h. Now P point is on the curve, so y coordinate of this point will be fx when the value of abscissa is x. Or we can say this height is fx. Then coordinates of point P are x, fx, and those for Q point are x plus h, f of x plus h. Here this height is f of x plus h. Now this distance is x plus h and this distance is x. So distance from this point to this point is h. Now join P point to this vertical line like this. Say this point is R. Here PR is parallel to x-axis. Suppose this angle is theta. Then from the triangle PRQ, tan theta is equal to QR upon PR. The value of QR from the diagram is, this PR is h. So we get slope of line PQ, that is f of x plus h minus fx upon h. We write this as delta fx upon delta x. The meaning of delta x, when the point was moving from P to Q, the horizontal moment is P to R, that is a change in value of x is delta x, and change in value of function is fx to f of x plus h. So we write here delta fx. So when we are moving from point P to Q along the curve, we have change in value of fx as delta fx and that of x is delta x. Now consider a situation when point Q is traveling along the curve to point P. It is traveling along the curve from Q to P like this. Suppose at one time Q point is here, P point is fixed here. We are not moving point P, only point Q is moving. This time if we join point P and Q like this, then we can see that this angle theta is changing, and also the length of this chord PQ is also decreasing. Also we can see that the value of this H is also becoming smaller. When Q point is very close to P point, is not exactly on P point, say very close to P point, that at that time we have chord PQ almost like touching the graph at point P. Okay, now here Q point is very close to P, they are not coincident. So we can say when Q point is approaching to P point, the value of H will approach to what? See, when Q point is exactly on P point, value of H will be exactly 0. But when Q point is very close to P point, the value of H is not exactly 0. In fact, it is approaching to what? 0. Suppose that time this angle is becoming, suppose, alpha. Now what is tan alpha? Tan alpha is slope of this blue line, and this blue line is in fact now what? Tangent to the curve at point P. What is in fact tangent? A line which touches the graph called what? Tangent. The seconds are what? The lines which are intersecting graph. Now from this, with the concept of limits, we say when limit H tends to 0, the value of tan theta is equal to limit H tends to 0 of f of x plus h minus fx by h. We have already this relation. In this relation we are applying limit h tends to 0 both sides. Now from the diagram, when h tends to 0, the value of theta is approaching to what? Alpha, or we can say theta becomes alpha. So we write this as tan of alpha is equal to limit h tends to 0 f of x plus h minus fx upon h. Here tan alpha is slope of tangent to curve at point P, and that is given by this formula, which is in the form of limits. Now when h is approaching to 0, we can say that this h, which actually represents change in value of x, is infinitely small. It is very small, and the very small quantity we express by dx. The meaning of dx, a very small change in value of x. And here this change will be also very small or infinitely small, and that change we write dfx. The meaning of dfx, the very small change in value of fx, and this ratio represent change in value of fx with respect to change in value of x. This ratio is called derivative of y is equal to fx with respect to x. So once more, let's see this diagram. In this diagram, when point Q is approaching to P, the value of H is approaching to 0. The angle theta of line PQ approaching to what angle? Alpha. And initially from triangle PRQ, we had this relation, tan theta is equal to this. This ratio is delta fx upon delta x, and when h is approaching to 0 or delta x was approaching to 0, this ratio becomes dfx by dx, which is called derivative of function with respect to x, and derivative we get by this formula. So derivative of function is actually what? Slope of tangent to the curve at point P. Now let's understand this happening from one video. Now see here, there are 2 points P and Q. Initially P and Q are joined like this. Now when Q point is traveling along the curve to approach point P, we have this type of view. Now you can see that Q point is slowly and slowly approaching to P, and here value of H is becoming smaller and smaller. Okay. And when point Q is very close to point P, we have line PQ coincide with what? This red line, which is in fact tangent to the curve at point P. Once again, you can see here point Q and P are joined, which is a secant. Now point Q is moving along the curve towards P. This H is becoming smaller and smaller, and when Q point is very close to P point, this secant is coincident with this red line. At that time, the value of this H approaches to 0, and the chord PQ is now tangent to the curve at P point. This line is in fact touching the curve at P point. Now consider this diagram. Now the height of point Q above x-axis is f of a plus h, and that of point P above x-axis is f of a. So this height from Q to this point where this pointer is moving is f of a plus h minus f of a. and this width from point P to this is h. Here we have taken abscissa of point P as A and abscissa of point Q is A plus h. Then coordinates of point P are A comma f of A, and those of point Q are A plus h comma f of A plus h. This height is f of A plus h minus fa, and this width is h. Now let's see the moving point Q on the graph. Now here Q is traveling along the curve towards P, and we can see that this height is decreasing, which is f of A plus h. F of A height remains constant because P point is fixed. Also we can see that value of h is becoming smaller and smaller, and when Q point is very close to P point, we have value of h approaching to 0, and at that time this line becomes tangent to the curve. Initially we had this angle theta, then tan theta is equal to this height, which is f of A plus h minus fa upon this width, which is h. But when h approaches to 0, we have limit h tends to 0, that of tan theta is equal to limit h tends to 0 of f of A plus h minus f of A upon h, and this is value of slope of tangent to the curve at point P. Find derivative of fx is equal to x square. Now from the definition of derivative, dfx upon dx is equal to limit h tends to 0 f of x plus h minus fx upon h. Now f of x plus since fx is x square, the value of f of x plus h will be, we replace x by x plus h, then we get x plus h square, this upon h. Then we have limit h tends to 0. If we expand this, we have x square plus 2hx plus h square minus x square upon h. Then we have limit h tends to 0, this x square cancel out, and we have 2x plus h. Now when h tends to 0, this value is approximately 0 and we are left with only 2x. So we can say derivative of x square with respect to x is 2x. This is actually rule of finding change in value of x square when there is a change in value of x. Suppose we have been asked to find slope of tangent to fx is equal to x square at point 2, 4. We know that the value of x is 2 here, then value of function will be 4, and this 4 is actually value of y. Or we can say 2, 4 lies on the graph of y is equal to x square. Now we have already proved that dfx by dx is equal to 2x. This is formula for finding derivative or slope of tangent to this curve for any x. Now we want this derivative at x is equal to 2. So when I put x is equal to 2 here, I get value 4. Now this 4 is actually what? Slope of tangent to curve y is equal to x square at point 2, 4. Here we can also write fx as y, then this is actually dy by dx. We know that y and fx are same. The value of fx are taken on y-axis. That's why we take fx as y. Let's see this on the graph paper geometrically. Now this is graph of y is equal to x square. Now here is point 2, 4. Now if I draw a line which touches this graph at point 2, 4 like this, okay, then slope of tangent at point 2, 4 is 4. So if this angle is theta, then we get tan theta is equal to 4. And when tan theta is 4, we can find the corresponding value of theta, from which we get this angle. Okay, consider one constant function fx is equal to 2. Now let's find dy by dx for this function. Now we know that graph of y is equal to 2 is a straight line parallel to x-axis passing through the point 0, 2. Let's see on the graph paper how is the graph of this line. Now this is graph of y is equal to 2. For any point on the graph here, the value of y is always 2 because this height is always 2. And this line is passing through this point which is 0, 2. Now, what is the meaning of dy by dx? That is change in value of y with respect to change in value of x. Now suppose x is changing from this value x1 to this value x2. When x was changing from value x1 to x2, there is no change in value of y because y is always same. So we can say dy by dx for this function is 0. In fact, for constant function, derivative is always 0. Okay, consider one linear function y is equal to 2x plus 3 or 2x minus y plus 3 is equal to 0. Now we know how to find slope of straight line. That is, m is equal to minus coefficient of x, that is 2, upon coefficient of y, that is minus 1, then value of m is 2. Now this is slope of this line, which is always constant. Now let's find slope using derivative. Now we have already seen that dy by dx represent what? Slope of tangent to the curve. Now by formula, dfx by dx is equal to limit h tends to 0, f of x plus h minus fx upon h. Then limit h tends to 0. What is fx here? That is 2x plus 3. And then what will be f of x plus h? You replace here x by x plus h. So we get 2 times x plus h plus 3. Then this is limit h tends to 0. If you simplify this, 2x and 3 gets cancelled out. We are left with 2h upon h. We can cancel out h because h is approaching to 0. H is not exactly 0. So we can cancel out h, which is in fact not 0. So this value is 2, which is constant. So we can see that for this function, slope of tangent does not depend on value of x, because here value is just 2. But in a case of y is equal to x square, the value of derivative was dependent on value of x. Now this is quadratic function, but this is linear function, and since this is not dependent on x, this is always constant. In fact, in the case of a straight line, we can say that at any point, what is tangent? If you want to draw tangent at this point, what will be that? This line itself. If I want to draw tangent at this point, then what will be tangent? Again the same line. And this line has slope 2. So we can say slope of tangent to straight line at any point is 2, which is in fact slope of the line.